All right, so let's try this one. I think we did one like this previously, kind of in general, but this one's got numbers now, so let's see if we can figure that out. So I'm going to need to find my reactions at A and B to get started. So first thing I'll do is draw a free body diagram of my entire structure, and I'll assume positive shear at A, positive shear at B. I'm going to replace this linear varying distributed load with a concentrated equivalent. And what is the equivalent force there? What's the area of the curve? It's a triangle, so 1/2 the base, 18 times the height. That's 36. So 36 kips. And we all know that the centroid of a triangle is either 1/3 from the big end or 2/3 from the small end. Either way, that will give you 6 feet on the right side or 12 feet on the left side. And I just need to find these reactions, which are shear forces. So I'm going to sum moments. This time I think I'll sum moments about B. That equal to 0. That's my equilibrium statement. So let's see if I can do that. So summing moments about B, this equivalent force of 36 kips creates positive or negative moment about B with right-hand rule. Positive, right? So the force is 36 kips and the distance is 6 feet. Now about B, the shear force at A creates what kind of moment about B? Negative. Are you guys out there? Are you there? Are you worn out? Too many problems in one day? No response. Excellent. Minus. So we'll have the shear at A times its moment arm, which is 18. So I should be able to solve for the shear at A. It looks like it's positive. It looks like it's 12. And then now I can sum forces in the y direction, make sure that's in equilibrium. And when I do that, I should be able to find my shear at B. So my shear force at A is up, that's positive in my sign convention. Shear at B is down, that's negative. My equivalent concentrated force is down, that's also negative. So I should be able to solve for the shear at B, and I get negative 24. So I have a positive shear at A and a negative shear at B. Let's kind of break that off from the rest of the problem, and let's draw the shear force and bending moment diagram for this one. So I'm going to start with the template. There's my starting line. There's my ending line. I don't see anything in the middle that would indicate any kind of abrupt change in shear or moment, so I'll just leave that for the time being. I'll assume a positive direction for X and a positive direction for shear, and I'll make all my shear values in kips. I'm also going to remind myself that the change in shear between any 2 points is the corresponding area under the load curve, and that the shape or slope of the shear diagram is given by the load. So starting here at A, what's my shear value? It's 12. Positive. And what's the shear at B? Negative 24. So let's see if I can make sure that this works out. So first of all, the change in shear between these two should be the area of the load curve, and the area of the load curve is So triangle 1/2 base times height, we already computed that. It's 36. And it's what? Positive or negative? Negative. So 12 minus 36 is, I lost my minus sign there, negative 24. So that's good. And what's the shape of the shear diagram? What's given by the load? So starting here at A, I go up, what's the load value? 0. So that means I have 0 slope starting here. And the value of the load increases to a maximum value of 4. Is that positive or negative? It's negative. So that means that here, I would actually have a slope, if you looked at it, it would be 4:1, negative slope. So now, I can match these two and get something that looks like that. Oh, look at this. We go from positive shear to negative shear, so we go through a 0 point. And we know that's pretty important because that location is probably going to tell us what about the moment. It's going to be, probably a local maximum or minimum. In this case, it might be the maximum. So I'm going to want that point. That's going to be an important point for me. So I'm going to say I need to find that value. I'll call it x1. And if I project that up, then I know that the area under my load diagram in this section, x1, is going to tell me how much this changes. And we already know how much it changes. If it starts at 12 here and it goes to 0, what's the change in shear? 12. So I'm going to come down here and write that. So the change in shear is equal to minus 12 kips. And what's the area under the load diagram in this same section? Well, it's going to be the area of this part of the curve. So it's going to be 1/2 base times, height. What's the height for any x? Can you write this as a function? Sure you can. It's a straight line. Starting at x equals 0, it's 0. So that means the intercept is 0. What's the slope of this line? Rise over run. Looks like 4/18, which is 2/9. So that means that anywhere on this curve, you're going to have 2x divided by 9. And you can check it. At x equals 0, you get 0. At x equals 18, you get 4. Oh, I didn't give myself enough room. I'm off the scale. Let me shrink it down here a little bit. There you go. Now you can see it. So what's the area of this part of the curve? It's going to be 1/2 x1 times 2x1 over 9. So 1/2 base times height. And the 2's cancel, and you get x1 squared over 9. So remember, these two things are equal. That's negative, by the way. So that means that I get an equation that says x1 squared over 9 is equal to 12. So that means that x1 squared is equal to 108. Multiply both sides by 9. And what's the square root of 108? I don't know that off the top of my head.
10.4.
Is that what 9 times 12 is? That's 108, isn't it? Is that right?
Yes.
Yeah.
Yes.
So what'd you get? 10 point what?
10.4.
10.4. So I now know what that distance is. Okay, so let's see if we can build the moment diagram. So I'll construct a positive value for x, or assume a positive direction for x, and also for moment, and all these will have the units of kip and feet. What is the moment at A, our starting point? 0. What about the end? Do we know something that's happening here at the end at B? Also 0. And now I'm going to project down that value that we just found. That was 10.4. And the change in moment, remember, is given by the area under the shear diagram. And of course, the slope of the moment diagram is the shear. So the area under the shear diagram, we mean the change in moment. What's the area under the shear diagram over this first chunk here? Well, conveniently for us in this problem, this is a nice parabolic section. And the area of that is 2/3 the base times the height. So 2/3 base is x1, which is 10.4, times height, which is 12. Somebody calculate that for me real quick. 83.2? So it's a positive area, so we're going to add it up. There it is. We also know that the slope is equal to the shear. And starting here at the beginning, our shear is 12 and positive, so it's going up. And it gets smaller and smaller till it gets to 0. And there's our 0 slope. So I can kind of sketch in what the cubic part of this curve would look like. So far, so good. It is a little bit of a stretch because you'd have to know this parabolic section area. But now the problem becomes is what's the change in moment from 10.4 to the end of the beam at 18? What should be the area of this part of the curve? If you look at that carefully, I don't know what that is. That's not a parabolic or a spandrel section. Neither end has an asymptotic slope, so I don't know what it is. So I can't do it. And you probably can't do it either. I imagine if we could do it, you'd get a negative area that's equal to 83.2 and it'd bring you back to 0. But I can't. So this is a disadvantage of doing it the graphical technique, is you might encounter some areas that you can't just by geometry know the areas. So I'm just going to have to stop here because I can't go any farther. I wanted to show you one that kind of misfires a little bit. Now, can we solve this problem another way? Oh, sure. Can you write a set of shear force and bending moment equations across this structure? Yes, you can. And if you were to plot them, you would get this curve and this curve, plus you know the other piece, which I can't get graphically. So when we do shear force and bending moment diagrams, the graphical technique, these triangular varying loads can cause problems. But for any combination of point loads and uniform loads and just about any combination you can imagine, this technique works great. So as you go through this class, you'll find yourself making these choices. You'll have to look at the problem and what's being asked, and you might have to apply a different method or a different tool depending on the advantages and disadvantages of that tool. So we'll stop here.